So we're going to start with a little shot while everybody gets seated. Chili pepper liquor. Okay, so hello everybody, and thank you for coming to our talk. We're going to be talking about some research that we did at Argus. Raziel and I both work at Argus. And it's kind of an interesting research with some things that look trivial, but some that don't. And at the end, we're going to tell you why we did all that. This work was actually done by more than just the two of us. So this is Razi. Say hi to them. And this is Shir. Shir was doing the signals intelligence. Razi is the radio guy. This is an IKEA clothes hanger. Don't ask. We'll get to that later. It does play a part in the research, and I'm somewhere in the back running the stuff. Yes. So, TPMS. Who's familiar with TPMS? Who knows what TPMS is? Okay, you did your homework. That's nice. So that's basically a device that measures the amount of pressure that you have in your tire. There's a number of reasons you want to do that. It affects your fuel consumption, the performance of the wheel. If you have a flat tire, you want to know. It can cause an accident, and so on. This is actually a device that is inside the rim. Okay? When you fill the air, it goes through that, and it has a little battery inside, and it measures the air pressure, and it tells the car. There is a receiver, an ECU inside the car that knows how much air you got. Now, we're not the first to look into that. This has been extensively researched. This device is not encrypted. Many people looked at that, reached the conclusion that you can spoof it, and we're not the first to do that. However, almost everybody, or not almost, everybody who looked into that reached the conclusion that while it is not encrypted and can therefore be spoofed, there is really not enough that you can do with it. So it's most of the time it's harmless. You can possibly cause someone to pull over, right? If they think they have a flat tire, they're going to pull over. Then maybe you can steal their car or rob them. That's one thing. If you have a self-inflating tire, then you can cause overinflation. That could be a problem, but very few vehicles have that, mostly military or maybe some big agriculture ones. And the general consensus is that this is mostly harmless and the potential for damage is really small. And when you tell us that the potential for damage is really small, we're like, yes, let's see. Now, this research was inspired, or the direction that we took was inspired by this video. We getting sound here? So this is a great commercial, and it made us, think. What if we could cause this sort of distraction on a larger scale? Because if it's just one driver, not a lot can happen. Everybody is agreeing on that. But what happens if you can do it on a larger scale? So, here's the plan. When you're dealing with one vehicle, we're flickering. Yeah, party. Guys, video, flickering. So when you're dealing with one car, this is basically what you have to do. You have to receive the transmission. You have to decipher what's in there. Analyze it, parse it, use radio equipment to do that. Then you need to modify the field that says how much air pressure you have. And as it turns out, not just that, there's a few more interesting details there. And then you have to retransmit. If you can do all that, then you will have spoofed a TPMS message, and then you can make the car think that you're low on air, right? But we want to do it at scale, to do it for more than one vehicle at the same time. Now, this is what you're looking for. This has been researched before. This is what a TPMS message looks like. One of them anyway, there are many types. So you can see that you have here not just the air pressure, but a very important piece of information, the ID of the wheel. Every single wheel in the car will have their own ID. So you can't just broadcast a random message. You need to know the particular wheel ID in order for the car to respond to it. So that brings the level of complexity a little bit up. And you also have, temperature, which you might not care about, and other flags, and there's a CRC. So once again, you need to know what you're doing. You can't just change values and retransmit. That's not going to work, and this is why a little bit of research is required. So scaling back up, we need to position multiple receivers. Why? Because the signal is not constant. The TPMS transmitter will transmit anywhere between once every 15 seconds to up to 2 minutes, depending on the configuration. So if I want to receive the TPMS transmission of Razi's car, I don't know where to wait. Maybe he just transmitted now, maybe it's going to transmit in 30 seconds, maybe in a minute, right? So imagine a long stretch of roads, you have to position multiple receivers. At some point, one of them will receive the signal. You have to collect it, analyze it, and know what you have to change in many different types. And then you have to aggregate all of them, okay, of all the vehicles, because what we want to do is retransmit them all at the exact same time. This is kind of a challenge. So this is the attack scenario. Anybody here from Denmark or Sweden? This is the bridge between Denmark and Sweden. So imagine the traffic coming from that way to this way. You buy the receiver. This is called the RTL SDR. You can buy it for like $9 on eBay. Really cheap. It can only receive, but it's good enough. And you position, let's say, 8 of them over this stretch of road. I don't remember exactly how long it is. I think 4, maybe 5 kilometers. So it takes more than 2 minutes to drive over that. So any single vehicle that enters this stretch of road will transmit a TPMS signal at some point during the travel, and we will receive that. Okay, maybe one, maybe more than one, but it's going to happen. And then you buy this device. The Yardstick 1 is a transmitting device as well. So this is a little bit more expensive. What was it, like $100, $130?
Yeah, something like that.
Something like that. And you put the transmitting device here. This is a tunnel, okay? Now imagine that when all the vehicles come here, a bunch of vehicles traveling at 120 kilometers an hour, and then 30 of them get this little boop, and the light goes on. You make 30 cars do that, I don't know, 3 drivers will take their eyes off the road. One of those might be, starting because they're not looking at the road. That's all it takes. In a tunnel, it's going to be a big problem. Now, I know I'm the bad guy now, but we're the white hat. I didn't get a white hat. I got a black hat this year. So, status report. We succeeded, but there was a lot of failure on the way. Okay, it didn't just all go very smoothly. And why? Because Razi and I decided that even though this was already researched, you could find pretty much 90% of what we wanted to do already done. We haven't done that yet. So we wanted to create for ourselves a learning experience. And this is very important for you guys. If you just copy from, other people's work, you miss all the stages of learning and experiencing and experimenting, which is very important. So we knew that we're going to reinvent the wheel. We're going to do things that other people had already done. And the meaning of that is that it's going to cost us time. This will take a lot longer than it could have taken if we've just taken other people's work and done it. But that's the route that we chose because we wanted to learn something that we hadn't done before. And Razi will tell you about what we've learned.
Thanks, Inbal. Yeah, so I'm going to tell you a little about all the stuff that we did and all about the mistakes we did, but also about the good stuff that we did as well. So the first thing was to take a vehicle and start exploring it. And then when we decided to start the research, Inbar said, well, no problem, I have a TPMS system in my car, we can just explore my car. And then we went down to the underground garage where Inbar's car is located, and we took an SDR, and indeed we started recording. And then the first signal we found is this signal. Now this makes a lot of sense, right? I mean, there are 4 tires in a vehicle, and there are 4 transmissions here. Although there are transmissions in several frequencies, but back then we thought, oh, maybe those are artifacts coming from the fact that we misused the SDR, or because there is some kind of retransmission mechanism that we are not aware of. I remind here that we didn't want to physically touch the car. We wanted to be able to explore the car remotely. So we started researching this signal, but then after a few minutes, we found another signal. And this signal also makes sense. And not only it makes sense because we have 4 transmissions, we also have something that looks like an invoking transmission, right? And then at this point, we started to be a little confused. And sometimes these transmissions sometimes we seen them, sometimes they were gone, and we didn't exactly know what to do. Now, I'm not sure if you are able to understand from the spectrum, but these signals are pretty strong. And not only strong, we were actually sitting next to the car and trying to do this recording.
This is my car.
Yeah, this is in Basca. So after seeing multiple signals and after since we were really confused, at some point we wanted to we said, okay, let's take the vehicle out, let's start driving around and see what we can find. And then it became even more strange because when we got out, there were no signals at all. So Inbar said, okay, enough with this nonsense, I want to take a shortcut. I'll go to the shop, I'll take the sensor out, we'll take a photo of the label on it, then we can look it up online for the specs, and then we can find out what the hell is going on here. Only thing is, Inbar car doesn't have
TPMS
sensor
at all.
Okay, so imagine our surprise here. Okay, never mind, we recovered pretty quickly, and one of our colleagues gave us his car, loaned us his car, so we can research it, and then we said, okay, so let's take that shortcut. Let's take the new vehicle to the shop, take the tire pressure sensor out, and research it. And this is how the label looks like. And in fact, that was pretty smart move for 3 reasons. So first of all, now we know there is a tire sensor in the car, right? But the second reason was that because of that, we were able to actually record the signal in an isolated environment. Instead of recording it in an underground parking lot, which was obviously stacked with other signals or somewhere outside, we just took the sensor into the shop and it was quite isolated, so we were pretty sure that we only record that signal and it helped us isolating the signal down the road. But the third reason was that since we only recorded one wheel, we also had recordings of one ID. And as Inbar explained, we wanted to extract the ID. So down the path, when we wanted to try and identify where the ID is located in the signal, that helped us a lot. So after we got the label and we got the FCC ID, we looked in online, and obviously that made things much easier for us. And we also managed to actually get the specifications of the signal as well as finding out all kinds of new information we weren't aware of. So for example here, you can hardly see, but we found out that there is a distinction between how the vehicle behaves where it is in parking and between when it is in drive. So again, this helped us understand more, and obviously after that it was quite easy to find the signal. So you can see those 4 transmissions, and this is the baseband view of the signal. Then we could extract all the information. And indeed, from the documentation online and from what we saw on the vehicle, we could extract the following information. This is not different from previous researches. It's only something that was unique to our sensors and help us down the path with the analysis. So at that point, we were able to quickly build a receiver. Now at that point, we still didn't have all the information, so we couldn't build the entire receiving chain, right? So what we did here, we did just a basic, we used a basic receiver, we used some energy-based detection of the signal, then we separated the signals the transmissions that we received to different files, then we did all the rest of the chain, extracting the bits and determining whether it is a TPMS transmission or something else manually. And at that point, we got a lot of recordings. And at that point, we used the fact that we have a lot of recordings to do some statistical analysis. Now, statistical analysis means that I have a lot of packets, so I can try and find out all kinds of patterns in the signal. And sometimes we used just common sense, stuff that helped us, and sometimes we use something that is more complicated. So the most basic one, and Inbar did it like a minute after we got all the recordings, it just replaced the ones and zeros in dots and lines, right? And it looks maybe dumb or maybe, I don't know, funny, but when you look at it closely, you can really see different patterns. So it really helped us guessing where the ID is located, where other information that we estimate is static is located, and where there is no static information, so for example CRC, right? Because CRC is also, it's not deterministic. Something a little clever that we did is we used the fact that this signal uses Manchester encoding. Anybody knows Manchester encoding here? Okay, not a lot. So one of the main characteristics of Manchester encoding is that there are some patterns that are legit and some patterns that are not. So 0, 1, 1, 0, 1, 1, 0, 0 are valid packets, but for example 0, 0, 0 or 1, 1, 1 or longer repetitions are not valid. This helped us both realizing where the packet ends and also finding out whether this packet is corrupted or not, and so on. In other things, we stood on the shoulders of giants. We didn't try to actually reinvent the wheel, but we did use some previous work, and we built upon it. So, for example, to find the tire ID. We used previous research that had some scripts that did some some statistical analysis, and we built our own script, for example, to find the tire ID. So what we did here is that we knew, or we guessed, that the tire ID is 32 bits, sorry. And then we took a sliding window, and we looked on every 32 bits window inside the transmission, and then we asked ourselves how many unique values there are through all the transmissions, through all the recordings that we had. And finally, we found out one window that only had 4 unique values, and that gave us a guess where the ID is, because obviously there are in the vehicle only 4 valid IDs for 4 tires. And another thing was finding the CRC parameters. So again, here we used something that already exists. We used the brute force CRC library that is available on GitHub, and perhaps it doesn't say much to a lot of you, but this actually is the information that we needed in order to be able to rebuild the packet with the right CRC values. Okay, with that information, we were able to extend the receiving chain and actually start parsing packets from the air, right? So this is exactly what we did. And we built something that automatically, as you can see, automatically detects transmissions, and then after a few seconds or a few milliseconds, it displays the received transmission. And you can see it looks quite nice here, right? It parses quite nicely. And the reason for that is because I did that in my lab, on my lab bench. When we went out and we started receiving transmission over the air, now it doesn't look quite nicely, right? So we have a lot of packets here that are corrupted, and we have a lot of stuff here that longer or signals that are not related at all to TPMS sensors and so on. By the way, another funny thing is that you don't hear me, you can see me speaking in the video, and you can hear an audio. This is for the plain reason I forgot to turn the microphone on. So, okay, moving on. So we wanted to make sure that we are actually able to receive signals from all the vehicles. As Bar explained, we wanted to take a highway or somewhere with a lot of vehicles and receive all those transmissions. Now, we took so we thought about a highway. So a typical highway has 6 lanes. Every lane is like about 5 meters. And we wanted to make sure that we can receive from approximately 30 meters. And then we did some theoretical calculations, and we found out that theoretically we could receive from hundreds of meters. So we were lazy. We said, okay, so Argus offices are watching just over Ayalon Road on Israel, which is one of the busiest highways that we have. So we said, okay, let's be lazy. Let's sit in the office. Let's take an antenna. And here's where the code rec took a major place in our research. And we can just tilt the antenna towards the highway, and then we can receive everything, and we are in the air condition, and we are happy, and we can just sit and hack cars. But unfortunately, this did not work, right? Because for some reason, we were not able to receive those signals, probably because of other interruptions, because there was a lot of metal outside of the building. You can see that the windows themselves are made of aluminum. And eventually, we had no choice, so Inbar had to get to the side of the highway and do the measurement there. But once we did that, we were able to actually receive those signals. Next was spoofing the signal, okay, and that was also a challenge. So at the beginning, we said, okay, let's do a very, very simple replay attack, right? Because we want to divide we wanted to reduce the risks, and we say probably if we can receive and record a low pressure signal and then replay it after we inflate the tires back, then probably we will have a low tire alarm. And we used, for that purpose, we used the HEC RF, so that is able to both receive and transmit those signals. The problem was that it didn't work. So for some reason, when we recorded the signal, tried to replay it in the vehicle, it just didn't work. Later on, we found out that probably because there is a difference between whether the car is standing and in the move, that probably was the reason why we weren't able to do the replay correctly. However, the problem with that method was you cannot debug it, right? You just record a signal, you send it again, it either works or not, right? So we said, okay, let's try to do something maybe a little more complicated, but a way that will allow us to actually debug the entire process. So we threw the HEC RF to the side, and we took the Yardstick 1. Yardstick 1, to those who don't know, it's actually a radio that can be controlled by a pretty simple Python interface. And again, we said, okay, let's work on the bench before we get down to the vehicle. Let's make sure that everything is working on the bench. Then we'll get to the vehicle. And indeed, it worked. And you can see here, the tire pressure, it's in PSI, and I'm not sure if you know, but there is no 101 PSI in a vehicle. That's very problematic, and obviously this is because we were able to spoof the tire pressure. Okay, moving on. So we were pretty happy, right? Because that was one of the main risks that we had. We wanted to be able to transmit to a vehicle and spoof the signal. So we went down and we said, okay, let's try to experiment with the transmitter. Let's try to find out how far we can transmit the spoofed signal. And you can see in bar here, we went down to the underground parking lot. And we used again the code track with the directional antenna, and you have the setup here. And again, you know, when you reinvent the wheel, you find out all kinds of crazy stuff. For example, the code did not run in Bar's computer for some reason.
And it's not running on the computer. It's a Python command you send to the yardstick 1.
Yeah.
The computer plays no part in this.
And in Bar and I have basically the same laptop, right? I mean, he has a MacBook, I have a little, maybe a little older MacBook, but for some reason, it just did not work. So eventually, we had to use my laptop, and Inbar was pretty frustrated, and we didn't find out the reason yet, but hopefully we do that in the future. So, after all these failure descriptions and after all that stuff, let's show you what really happened. Just before I play the video, I'm sorry we couldn't actually take a video of take a good focus of the details. However, when there is a low tire pressure, the screen here will turn to red. So pay attention.
Okay, ready?
Yep.
Start now. Okay, awesome. It's working.
So at that point, we were able to receive TPMS sensor transmissions from the highway. We were able to successfully spoof a vehicle from over 30 meters, so that parking lot was pretty large. And we tried several scenarios. We tried taking the vehicle from the sides and so on. Everything worked pretty great. And we succeeded in stripping a received TPMS transmission, rebuild it with our own tire pressure value, and then retransmit it. So currently we're working on the backend setup. So as Inbar explained before, we want to really scale it up. So for that purpose, we need to be able to take those transmissions, those received transmissions, rebuild the packet, send it to all those transmissions on the bridge, and then send it back again. So we're now working on that. Because we are going to use a very simple VPN setup, this will help us scale up the entire setup pretty quickly, and this indeed already working, and we're just finalizing that setup. Okay, what's next? So we have a few challenges here. The first one is to be able to handle multiple transmission methods, multiple modulations. This one was based on a frequency modulated signal. However, we know that there are some sensors that use amplitude-based modulations and so on. So we need to take care of that. Obviously, we need to find out how other sensors work and how they are built, and to be able to parse them correctly, and to be able to synchronize everything. So as Inbar said, we need to be able to receive everything, aggregate everything, and then transmit everything on the same time. So this is another challenge that we're still facing. Okay.
So as responsible security researchers, I told you I didn't get my white hat, but I actually have it. You cannot disclose a problem or tell the world something is wrong without offering ways to solve it, right? Because otherwise you just gave the bad guys ideas and weapons. Obviously, okay, the #1 problem here is that the signal is not encrypted. So the trivial thing to say is, let's encrypt the signal. But here's a problem. This is the TPMS. It's really small. It's running on a small battery. This is not a real computer. So if you have to do encryption, you might need to get into costs. The whole design of this thing might need to change because the architecture or the microelectronics inside are not strong enough to do the encryption. And also, how do you synchronize the keys? What happens if you change the tire? So now your car needs to know the new wheel, or maybe the new wheel needs to know the encryption key for the car, so this gets complicated. This is not really a viable option. Also, one thing you could do to mitigate the problem, right now the vehicle is listening to the wheel. So whenever the wheel is speaking, the vehicle is listening. If you change that and you said, okay, from now on, I don't care what the wheel is saying unless I ask it first. Hey, wheel, how much pressure do you have? And then it tells me. Then that would make the attack significantly harder, because I would have to listen to the question and then get into a race condition with the wheel and answer over the wheel, right? That's really a lot more complicated, and it might not even succeed, right? But actually, the best way to mitigate with existing hardware is to correlate the signal with other sensors you already have in your car. For example, all modern vehicles have a sensor that tells them how fast the wheel is turning, right? Because it's used for skid alert and ABS. So when the tire changes significantly, the rotational speed changes as well. So if you get a low tire alert, but the wheel is still turning in the same speed, at the same speed, then you know something is wrong. You cannot trust the pressure. And there are other ways to do that. Some passive TPMS actually look at the balance of the car. If you have a low tire pressure, then one side of the car is a little bit lower. So you already have existing sensors and signals that you can correlate with and know if this is a fake signal or not. But of course, it's hard for us to tell the car manufacturers how to fix their problems, but the number one problem is us. We need to keep our eyes on the road. If we knew for a fact that whenever a driver got an alert, they would still look at the road, this entire attack wouldn't work. Okay, so as always, it's like security people like to say, the technology is okay, it's the human, right? So this is just an example. Now, that was the research, and here comes the message, okay? It's doable. Yes, it's a little bit far-fetched, but imagine if that thing actually works, then people might, get hurt. A car crash inside a tunnel, that's a serious thing. So it's doable, and it only needs to happen once. Imagine it just happened, and someone is calling one of the car makers and says, I did that. I want 3 Bitcoins by tomorrow, or it happens again. Who knows? Maybe they're lying. Maybe they're not lying, right? So it's doable. This is not something to be disregarded. As hackers, we know that where there's a will, there's a way. If I want to find a way to make something malicious, I will find it. And this is why our starting point was the fact that everybody else thought that this was harmless. This is sort of a challenge accepted. Because when something is harmless, then you already predict that there are not going to be any mitigations. So if you find a way to do something, the chances of creating damage are larger because no one was even prepared for that, right? And we changed that saying a little bit to say, where there's malice, malice is bad intention, okay? Where there's malice, there's a way. When the bad guys decide that they want to attack something, they will invest the time, money, effort, whatever, and find a way to attack. So we should never underestimate the ability of other people to find things that we have not found. And this applies to all of us. As researchers, if we didn't find the answer, it doesn't mean it's not there. If we performed a pen test, it does not mean that we found everything. Somebody else could find something that we did. Okay, so remember that. And as someone that I sometimes meet over the conference calls of the SAE, he said it's also the other way around. If there's a way to do it, someone will be malicious. Because that's how the world works. Okay, because of the incentives the criminals have, or just script kiddies, whatever. Someone will always be, pardon my French, the asshole who wants to ruin the party for everybody else. So never assume that everybody is a good person. And maybe the most important lesson here is that scale matters. If you look at a single car, okay, this behavior is by design. Low tire pressure, sounds an alert, and makes some notification on the dashboard. That's expected. You can't say, hey, this is wrong. This is expected behavior. And the risk, indeed, is meaningless. The worst that can happen is maybe you pull over and discover that you don't actually have a flat tire. But when you do that at scale, all of a sudden the threat and risk assessment change. All of a sudden something that was insignificant before becomes significant now. So when you do threat analysis and risk assessment, you need to be aware of the fact that maybe what you're looking at doesn't mean much when it's one system, but what happens if it's done on many systems at the same time or sequentially? Scale matters. Scale changes the risk score of this particular scenario significantly because we could theoretically cause a car crash. Failure. We come from Israel. In Israel, failure is part of the learning process. Some cultures in other places around the world don't encourage failure. In fact, some of them even discourage it. But we are researchers. Research is about failing. Many times people will stand on stage and show you what they did. Amazing stuff. Best research ever. But they don't tell you how they got there. What they tried that worked, what they tried that didn't work. What was their thought process? Learning from what other people did is like doing copy and paste from, all the websites with the solutions. But learning somebody's thought process teaches you a lot more. So you need to teach others as well. Failure is okay because I think it was Mark Twain who said, I failed all the way to success. Okay? And if you haven't watched this talk, Angie Albertini, a very appreciated researcher, gave a talk 2 years ago just about this, success and failure in the INFOSEC. So look it up, it's probably on YouTube. And it's part of the process, you have to accept that. And if you fail, do not give up. It's part of the process. Document it, continue researching, and then help others. Thank you. I think we have time for questions, right? Yeah. We're keeping
Thank
schedule.
you so much to both of you. Yes, we do have time for questions. And hands are popping out. Mics are coming to you. Just let's start anywhere.
Shouldn't the car automatically correct itself? You send the message that the tires are deflated, but the sensors send the message that the tires are not deflated, so the car should automatically correct for the erroneous behavior that you introduced.
But a single car is a single case. And in the case of a single car, nothing is wrong here. As I said, this is expected behavior. By design, when the tire pressure goes down, then an alert happens. If you discover that the tire pressure is back up, for instance, if I spoofed the message and I got the alert, but you continue driving and then 20 or 30 or 60 seconds later, the real signal is transmitted, then the alert goes away. It's very simple. Alert, display. Alert, display. The problem is at scale, and until we have a good vehicle-to-vehicle infrastructure working, then you can't take that into consideration. There's very little you can do. This is expected behavior. Did I answer? All right. Anybody else? Yeah, we're also going to look at the back because it's always the people in the back that don't get to ask. Do we have another microphone for the people in the back?
Hello, thank you for your presentation. What car makers how car makers mitigated that risk?
Well, actually, car makers have some other concerns besides the security concerns. So one of the things that TPMS sensors have, they require a lot of maintenance. If you want to replace a tire that is broken, there is like a whole process of scanning the new tire, updating the software on the ECU in the vehicle in order for it to be able to transmit and receive. So basically, they are already looking for ways to avoid using IDs such as automatic recognition of the sensors in the vehicle, and also relying on other sensors in the vehicle in order to determine whether the tire is really deflated or not. So we assume that in the future, this will be solved not because of security concerns necessarily, but also because of a lot of maintenance concerns as well.
And of course, we hope that they do the correlation with other sensors, as we've suggested.
Don't you consider that the car is over-alerting the driver?
So one of the things that you hear now on the SAE meetings is that Driver distraction is beginning to be taken into consideration both in terms of security and safety. The industry is mostly interested in safety because you sell somebody a car, they need to get where they need to get, right?
But it's very unsafe to alert the driver for inflating of the...
I'm not a car maker, okay? And as I said, this is an expected behavior.
Okay.
Because if you have a flat tire, that has implications. You want to know. So if they correlate it with other sensors, it's going to be better. Or maybe they come up with a solution that we didn't think of. We don't pretend to have all the answers. Right?
Thank you.
There was somebody else at the back? Also, we're going to be outside if you need to ask us more things.
Hello. So I was wondering, you said about correlating
Where are
with,
you?
Over there.
Okay, cool. Yeah.
correlating with other sensors, but each tire will actually send its own data besides the data that you are sending, the fake data. So wouldn't it be simpler to just count the number of occurrences and don't display any alert if you get different information from the same tire?
Actually, it's the other way around. Actually, in this case, the spoofing transmission was pretty persistent. It took us actually a few seconds, as also like driving the car, accelerating and braking, in order for it to retransmit the correct signal again. So
But the tire doesn't send its own signal in the meantime?
the tire does send its sensors, but because of the way, eventually those tires run on batteries, right? So in order to save battery life, they don't transmit all the time. They transmit sometimes once a minute, and sometimes they only transmit when you accelerate pretty quickly, or if you brake pretty quickly. And this is something that we took as an advantage for the spoofing attack. So eventually, what happened here in the video is that once we sent the spoof message and the low tire pressure alarm turned on, it took a few good seconds before the vehicle got an update transmission from the tires. And again, this is to save battery.
Having said all that, by the way, anomaly detection is one of the ideas, but it's easier said than done. It is, though, one of the ideas.
Yeah.
There was someone here? Microphone?
Yes, the mic is coming to you. Just, yeah. Keep your hands up so we can see you. Cool.
Hey, and I don't mean to put you guys down on this. I love
Feel
your
free.
work. Have you guys considered the Barbra Streisand effect in that you mentioned that basically offering solutions on mitigation is important, but have you reached out to any vendors or any entities to basically say, I could probably use this as an assassination attempt for like officials or like on a motorcade or something on a highway with like a 30% success rate, in that to like put it into context where it could have the most damage or the most efficiency? Or have you tried contacting any vendors that particularly make these to say, this is how it could be, or at least officials that say, this is what the worst case scenario would be for you guys?
So I'll answer in parts. As I mentioned before, we're on one of the conference calls of the SAE, where people from the entire industry are there. We discussed this and presented our theme. Please remember, the point of this research is not the actual scenario of the TPMS. The important thing here is that when you do risk analysis and threat assessment, or threat analysis and risk assessment, scale matters. So now you need to reconsider the risk score for something that looks riskless now, but might look different if you put it at scale. Actually, you were talking about assassination of seniors. They have their own, I forgot the word for that, but...
Auto-inflation?
No, they have, it's like 3 cars.
Yeah.
There's nothing, motorcade, there's no one to crash with. And I'm pretty sure their drivers are much better than any of us. So that is not really a scenario.
Which is true, but they're still human, so they're still going to have human reactions like an alert.
Yes, but it's really far-fetched, and yes, there is a chance that this will be performed. But that is something that you can say about pretty much all the research that we do. All of us who disclose problems or talk about risks, you never know whether you predict the future or create the future, right? Because maybe some of you are black hats. I don't know. That's possible. It's always a risk. But this is so far-fetched, yet possible, that we felt comfortable to display that, talk to the vendors over the industry over other channels, and they all agree that while this is an acceptable behavior, they need to reconsider threat analysis at scale.
Thank you.
We're out of time. One more?
Or about 3 more questions.
All right. Who's up next?
So go for it.
Somebody here, front line. Microphone, over here. There it is. Or you could shout and we could repeat the question. Yes?
The spoofing test that you've done in the parking lot was done with a predefined transmitting package, or did you intercept and did you receive some packet from the car and then change it and send it back?
So we did the entire process of intercepting, rebuilding, and transmitting. It was divided into 2 steps. So we didn't actually make the entire thing online. And indeed, it's a researching process. So we still need to, as we said before, still need to take care of the synchronization.
So you sent a predefined package
So it was
in the blind.
Yes.
It wasn't entirely predefined. We were building the package through the script where you chose the pressure and the packet was being built and sent. The CRC was being calculated. The reason we didn't do what you asked about is because we were doing our experiments at a parking lot. And as we said before, sometimes the TPMS will transmit every 60 seconds. So you can't drive around for 60 seconds waiting for that. That's not part of the research. So we recorded the message at one opportunity and then at runtime modified it, recalculated the CRC, and transmitted it. So it's not really, it's a lab setup, basically.
It's
but
not a man in the middle.
Yeah.
Yes.
process.
Sort of.
It's not.
You can do the entire process in a parking lot. You just don't have enough room for the car to drive, enough time for you to record it because of the frequency of transmissions, and then send it. You just don't have enough length.
That was an extra. Like what we did still proved the research.
Okay, thank you.
Anybody else? Somebody here with the... Have we considered the implications on autonomous driving? We haven't yet. This is pretty much the same question of how to analyze signals that you're getting from sensors, whether you do anomaly detection, whether you correlate them. I'm assuming, it's hard to tell, but I'm assuming that car vendors that make autonomous vehicles that watch this talk or are part of this discussion that we have on the conference call will know to take this into consideration, because this is a particular case of a false signal, but when you start talking vehicle to vehicle, then it's also a trust problem. Do I trust Razi's car if they're telling me that they're braking right in front of me and they're not? Then I start braking and then they brake. So it's a trust problem that the industry is aware of and they're looking into that. Last one, I think.
Yes, last question.
Any hands? Over there, front line. Row line.
Hi, I have a question. It's not technical, it's more of, I don't know, an opinion. You mentioned that car manufacturers don't want to invest more in the encryption part and change the device, but also you said that manufacturers want to increase the safety. What's more important to them, the cost or the safety?
That's a theological question. As I said, this, in the context of a single vehicle, is expected behavior, okay? And investing now in encrypting the TPMS doesn't really solve the problem if you can do it in other ways. Correlating the same signal with other sensors you already have can be done in software. So why go and invest money and time and research into making new hardware where the same solution can be done in software? So it's a mitigation. It's just not the best one or the most suitable or the cheapest, depending on, whatever. All right.
Cool.
Thank you so much for listening to us. If you have any questions, we'll be outside.